Lexi, and welcome back to your TP2 homework recap thing. We're in homework 3 now, and let's just get into it. This homework is about line integrals, curls, and parameterization of a surface. And there was just a single question that was like tangent planes. Find the tangent planes to the surface that you parametrized. Just a warning, I struggle with saying the word parametrization sometimes, so if I just completely butcher it, just ignore. So, line integrals. We saw that a line integral looked like this in the last homework, times dr or dl or whatever. So, for example, this is the most basic line integral. It's essentially just adding up little weighted bits of a line and then adding them all up together and getting the line. When you have the line integral of a scalar field, what you're doing is this is your line. You can search it up. I've just written curtain because it's essentially like draping a curtain over this. And that curtain is what you're finding. Now the line integral of vector field, I've written how much field and line agree. Because essentially it's like, I don't know how else to put it. It's how much field and line agree. It's like how your line moves through your vector field. Anyway, so here are your steps to doing a line integral. First off, you have your vector, position vector r. It's going to be parametrized in it's going to be like r of t or something. So as I discussed last homework, you have to find this by just finding the t derivative of r. And then you get your vector field in vector form. So that you can perform the dot product and then integrate. I mean, those are basically just the steps. Another special little point here is that if it's evaluated at specific points, you input the points into the vector field. Because we're only integrating over that specific part of the vector field, and it also makes it so that you're still, working with only your one variable. An example of that would be this question. We're looking at this part. We want to go from this point 0, 0, 0 to this point 1, 1, 0. This is our vector field, y ax by squared, and we want to compute the line integral. So we found a parametrized position vector using the sort of same technique that I discussed for the parametrization of a straight line in homework 2. And then here we take our vector field and we input. Sorry, my pencil just turned off. We input y is equal to t, x is equal to t, and y is equal to t into here, and then use that because we want it at that specific point. You know what a curl is? I'm not even going to get into that. Parametrization of a surface. When you parameterize a line, you're going to have it in terms of one variable. But when you parameterize a surface, it's going to be in two variables because of how surfaces work. It's just one extra dimension than a line. So there are examples, and I'm actually just going to go down in the homework to show you those examples. Here. This first question, I low-key did it wrong, but it's technically correct. So it's technically a way to do it. Essentially, here we have x in terms of the others. Now we can let x equal x, y equal u, and z equal v. So we sub in u for y and v for c, and now we have x is equal to this. And now if we input that into our position vector, we have x is equal to this, y is u, and z is v, where u and v are elements of real numbers. And here you can see that it is in fact in terms of two variables. In the next one, it's saying the surface this, x squared plus y squared plus z squared equals 18. If you look at that, it looks exactly like the equation for a sphere with a radius of root 18. So what you could do is you could just straight up use spherical coordinates. Please remember how to use spherical coordinates. And for this last part, we have a condition here, a boundary here, where z is between 2 and 4 inclusive. So we know z is here, rho cos phi, and since we know rho is root 18 or 3 root 2, so we could just sort of input that. So 3 root 2 cos phi is going to be between 2 and 4. You can manipulate the equation until you get what phi has to be between, and those are, that's like your domain, your boundary for this specific vector. And the last one is the cylinder, this y squared plus z squared equals 9. Now you can see, as we discussed last time, that this is a cylinder along the x-axis with a radius of root 9, which is 3. So you can use cylindrical coordinates. And since it's along the x-axis, your sort of linear, your non-sine, non-cos component is going to be the x component. So just, I used both z and x here to denote that. That was kind of silly. Doesn't really matter as long as it's in the correct component, because it's in the x slot here. Yeah. So those are some examples. And the last question, it was like how to calculate tangent to a surface, and it's using this formula right here. You can search it up. This is just a formula. You just sub things, and you just have your vector, your function, and you have your points, and you just sub it in. Anyway, that's it for homework 3.